Welcome back to another deep dive from Peaceful Rooster Experience. This time, we're going to be diving into the world of stream processing. You're curious about making sense of data in real time. We've got a stack of articles here, and we're going to break down the most important stuff.
Yeah, it's a very hot topic right now. Businesses are realizing that you can't just wait for data to pile up anymore before you analyze it. They need the insights, like right
Oh,
now.
right. Yeah, it's like the difference between reading yesterday's news and getting like live updates as events unfold.
Yeah, exactly.
Speaking of which, our sources highlight a fundamental difference in how data can be processed. We've got batch processing versus real-time processing.
Exactly. Match processing is like waiting until your entire inbox is full before you even think about sorting through emails. It works if you have a lot of time on your hands, like generating a monthly sales report. But for situations where you need immediacy, like I don't know, detecting a fraudulent transaction, like the moment it happens, real-time processing is a game changer.
That's a great point. Our source mentions a great example of batch processing in action, generating those detailed monthly bank statements. You don't need those figures like right away. So
Yeah.
batch processing crunches the numbers efficiently when the time is right.
Yeah, and on the other hand, imagine a system that can flag a suspicious transaction like the instant a stolen credit card is swiped. That's the power of real-time processing.
It's like having a superpower for security.
Yeah.
Our sources also mentioned different flavors of real-time processing. There's near real-time and true real-time. Is it all about speed, or is there more to it?
It's about acceptable latency. How much delay can you actually tolerate before you act on the data?
Ah. So near real-time processing with updates every few seconds might be good enough for, let's say, social media analytics, where you want to track, trending topics, things like that. But for something like air traffic control, where split-second decisions are, super critical, you absolutely need true real-time processing with basically no delay.
So real-time processing opens up a world where businesses can react instantly to changing circumstances.
Totally.
Our sources list they list a bunch of cool use cases for stream processing. What really stood out to you?
Well, besides the fraud detection we were just talking about, algorithmic trading is a great example. These platforms analyze market data in real time to make split-second trading decisions. It's like having a superpowered stockbroker working tirelessly just for you, you know.
That's definitely something that I think our learner listeners would be interested in. What about some more everyday examples?
So think about those personalized recommendations you get while you're shopping online.
Oh yeah.
Often that's powered by real-time analysis of your browsing history, instantly suggesting products that you might actually like.
It's amazing how this technology is shaping our online experiences.
Totally.
Any other cool use cases that our listeners might encounter?
Absolutely. Predictive maintenance is a big one. Sensors constantly monitor machines and equipment, and real-time processing helps predict potential failures before they even happen, saves businesses time and money.
Right.
Trend analysis on social media is another area where real-time insights are super crucial.
Okay, so we've seen the what and the why of stream processing. Now let's unpack the how, the architectures behind it all. Our sources compare these architectures to choosing a house layout, which I think is a brilliant analogy.
I love that analogy.
Yeah.
So let's walk through the options. First, we have the Lambda architecture. Think of a house with two separate wings,
Uh-huh.
one for batch processing and one for real-time processing. It offers the best of both worlds. The batch layer handles historical data for, big picture insights, while the real-time layer keeps you updated as things happen.
Yeah.
So it's comprehensive, but maybe a bit more complex to manage, like having two separate kitchens.
Exactly. So managing those two separate pipelines can be challenging, especially as your data volume grows. But when you need both historical and real-time data, Lambda can be a very powerful choice. A great example is an e-commerce platform that needs to track real-time sales while also analyzing long-term customer behavior patterns.
That makes sense. What about the next option in our source material?
So the Kappa architecture is all about simplicity and efficiency. Imagine one giant open plan space where everything is treated as a stream. Everything just flows through this single pipeline, which makes it much easier to manage and maintain. If you need to analyze historical data, you just replay the relevant portions of the stream.
So it's like having all your cooking, dining, and living areas combined into one spacious area.
Exactly.
It sounds efficient, but are there any drawbacks to this approach?
So Kappa's strength is also its potential weakness. It might not be ideal if you have very heavy batch processing needs or require complex historical data analysis. Imagine trying to bake a three-tier cake in that open plan kitchen. Sometimes dedicated spaces are better.
Right. So Lambda for when you need both batch and real time, Kappa for when everything's a stream. What's the final option in our blueprint for stream processing?
The data flow model focuses on the continuous flow of data. Think of it as a house where the focus is really on how you move between rooms rather than the rooms themselves. Data flow excels at managing this constant processing with a strong emphasis on windowing and state management. It's like having well-defined hallways and clear pathways to ensure a smooth movement throughout the house.
Windowing and state management sound pretty technical. Can you unpack those a bit further?
Sure. Windowing allows you to group data into time-based chunks like hourly or daily aggregates. It's like sorting your mail by date. State management ensures that your processing remembers where it left off, even if there are interruptions. It's like bookmarking your place in a book. You can pick up right where you left off.
So data flow is all about maintaining order and consistency in a world of continuous data. What are some situations where this architecture would be a good fit?
Dataflow is a great choice for applications that require complex event processing and need to maintain a consistent, reliable flow of data. A perfect example is a fraud detection system that needs to track user behavior over time and flag any suspicious activity based on predefined rules.
This is giving me a much clearer picture of the different approaches to stream processing. Each one has its own strengths and trade-offs depending on the specific needs of the application.
Exactly, and choosing the right architecture is a crucial first step in building a successful stream processing system.
Okay, so we've laid out these different blueprints for handling these data streams, but as with any construction project, there are bound to be challenges along the way, right?
Absolutely. Stream processing might sound, magical, but it comes with its own fair share of complexities. Our sources dig into some of these, and I think they're worth unpacking.
Perfect, because after that overview of the architectures, I'm ready to dive into the nitty-gritty. What's the first challenge that jumps out at you?
Well, one of the biggest concerns is fault tolerance. What happens if a server crashes or there's a network outage? You don't want your whole system to just come crumbling down.
It's like making sure your house has a strong foundation so it can withstand a storm. What are some ways that stream processing systems achieve this kind of resilience?
Techniques like checkpointing and data replication play a crucial role here. Checkpointing is like regularly saving your progress in a video game.
Yeah.
If you lose power, you don't have to start all over again.
That's a great analogy.
Mhm.
And what about data replication?
Data replication is like having backup copies of your important files. If one part of the system fails, you can still access and process the information.
So it's all about redundancy and backup mechanisms.
Exactly.
That makes sense. But what about speed? It seems like latency would be a huge challenge when dealing with real-time data.
You're absolutely right. Latency is the enemy of real-time processing. Imagine waiting, several minutes for your credit card to be approved at the checkout. Not a great experience.
No kidding. How do stream processing systems tackle this need for speed?
It's all about optimizing the flow of data. Efficient message queues act like express lanes for data, prioritizing urgent information and making sure it gets processed quickly.
And we also need to be able to handle the sheer volume of data coming in, right?
Yeah.
Especially with things like social media feeds or sensor data from thousands of devices.
Exactly. Data volume and velocity are massive challenges. Stream processing systems need to be able to drink from a fire hose without choking.
So how do they manage that kind of deluge of data? Do we just need bigger and faster computers?
It's more about smart architecture and distribution of work. Scalable systems like Apache Kafka and Spark Streaming are designed to handle this by distributing the workload across multiple machines.
It's like having a team of chefs working in parallel to prepare a massive feast instead of just one chef trying to do everything.
Exactly. And as the volume of data grows, you can simply add more chefs to the system to keep up.
Okay, so we've covered fault tolerance, latency, and scalability. What other challenges are lurking in the shadows?
Well, managing state is a big one. Remember those examples of tracking user behavior over time or analyzing patterns in sensor data?
Yeah, like remembering where we left off in a complex puzzle, or keeping track of all the ingredients in a recipe.
Exactly. To do that effectively, stream processing systems need to maintain a consistent view of the current state
Hmm.
of things, even as new data is constantly coming in.
So it's not just about processing individual pieces of data, but also about understanding how they relate to each other over time.
Precisely, and that requires efficient and reliable state management techniques. Solutions like RocksDB, which is a type of embedded database, provide a fast and robust way to store and manage those states.
It sounds like keeping track of state is crucial for ensuring accuracy and consistency in stream processing. What else do we need to watch out for?
Another big one is ensuring exactly once semantics. In other words, we want to make sure that each data record is processed, only once, even if there are system hiccups or errors along the way.
It's like making sure you don't accidentally charge a customer twice for the same purchase.
Exactly. And achieving exactly once semantics is a non-trivial challenge, but it's essential for maintaining data integrity and avoiding those costly mistakes.
So how do these systems guarantee that each piece of data is processed only once? Is there some kind of magical duplicate detector?
It's more about clever design and coordination. Techniques like idempotent operations and transactional message delivery play a big role here.
Can you unpack those a bit further?
Sure, an idempotent operation is one that can be executed multiple times without changing the final result. Think of pressing an elevator button. Pressing it multiple times doesn't make the elevator come any faster. It just ensures that it's registered once.
I get it. So even if a message gets processed, more than once, the outcome is the same. What about transactional message delivery?
That's like sending a package with deliver confirmation. You know
Yeah.
for sure that it either arrived safely or didn't arrive at all. There's no ambiguity.
So it guarantees that the message is processed completely or not at all, preventing those partial updates and inconsistencies.
Exactly. These are just some of the ways that stream processing systems ensure data integrity and reliability.
It's amazing how much complexity goes on behind the scenes to make real-time data processing work seamlessly.
It really is, and we haven't even touched on the challenges of handling late arriving data or managing time effectively in a continuous stream of information.
Well, those challenges sound like a perfect segue into some of
Yeah.
the common questions people have about stream processing.
Right. After all, with all these complexities, it's natural for people to have questions.
So let's address some of those FAQs, starting with one that popped up for me earlier. How do systems like Spark Streaming handle the problem of late arriving data? What if some pieces of the puzzle show up after we've already started putting it together?
That's a great question. Spark Streaming uses a technique called watermarking to tackle this problem. A watermark is essentially a timestamp that marks the expected completeness of data up to a certain point in time.
So it's like saying we're not expecting any more data from before this time.
Exactly. And any data that arrives after the watermark is passed is considered late and might be handled differently.
Does that mean that that late data is just discarded?
Not necessarily. It depends on how the system is configured. Sometimes late data might be might be processed separately or used to update previous calculations, but the watermark helps define a clear boundary and ensures that the main processing pipeline isn't held up by stragglers.
That makes sense. It's like having a cutoff time for submitting assignments. Anything that comes in late might be accepted, but it won't delay the grading process for everyone else.
Exactly.
Okay, another question that often comes up: if real-time processing is so amazing, are there ever times when good old-fashioned batch processing is actually a better choice? Is it always about speed?
That's a great question. While real-time processing is incredibly powerful, it's not always the best tool for the job. There are certainly times when batch processing is more appropriate and efficient.
Can you give us some examples?
Sure. Think about situations where you need to analyze massive historical data sets to identify long-term trends or patterns. For example, if a company wants to understand how their sales have performed over the past 5 years, they wouldn't use real-time processing for that.
Because you don't need to know those figures every second. You just need a comprehensive analysis of the past.
Right. Batch processing is perfect for that kind of analysis. It can efficiently crunch through large volumes of data without the need for real time updates.
Our sources also mentioned regulatory reporting and data warehousing as areas where batch processing is commonly used. Why is that?
So regulatory reporting often requires analyzing large data sets over specific periods of time, like quarterly or annually. And data warehousing is all about storing and analyzing historical data to support business decisions. Real-time processing wouldn't be the most efficient approach for those tasks.
So it's really about choosing the right tool for the job, considering factors like data volume, time sensitivity, and the type of analysis you need to perform.
Exactly. Both batch and real-time processing have their strengths and weaknesses, and the key is to choose the approach that best fits the specific requirements of the task.
Okay, let's tackle one more FAQ before we move on. This one's a bit technical, but I'm really curious about how stream processing systems ensure data consistency, especially when we're talking about maintaining state and handling those intermediate calculations.
That's a crucial aspect of stream processing, and it ties back to some of the challenges we discussed earlier, like fault tolerance and exactly one semantics.
Right. So how do these systems ensure that nothing gets lost or duplicated, especially when multiple processes might be working on different parts of the data stream simultaneously?
Several mechanisms work together to achieve this consistency. First, checkpointing plays a crucial role. By regularly saving the state of the processing pipeline, the system can recover from failures without losing data.
It's like having those regular save points in a video game. You can always reload from the last checkpoint if something goes wrong.
Exactly, and to ensure that each record is processed only once, exactly once semantics are essential. This involves careful coordination between the processing engine and the messaging system.
So if a message gets processed, multiple times due to a system hiccup, the final result remains the same.
Precisely. Idempotent operations and transactional message delivery are key techniques used to achieve this.
And to manage all this state information efficiently and reliably, systems like RocksDB provide robust storage and retrieval mechanisms.
Exactly. It's a complex dance of coordination and clever engineering, but it's what makes stream processing so powerful and reliable.
It sounds like maintaining data consistency in a real-time processing environment is a complex feat, but these systems are designed to handle it gracefully.
Absolutely. And as the field of stream processing continues to evolve, we're seeing even more sophisticated approaches to handling these challenges.
Okay, I think we've covered a lot of ground in terms of the challenges and intricacies of stream processing, but now I'm curious about the tools that are out there, the actual software and platforms that people use to to build these real-time data pipelines.
Right. It's like having a well-equipped workshop with all the right tools for the job.
So let's explore some of those tools, starting with Apache Kafka. It seems to be a popular choice in the in the stream processing world.
Kafka is a powerful distributed streaming platform. Think of it as a high performance message broker that handles the flow of real time data between different systems.
So it's like the central hub for all the data streams.
Exactly. It's known for its for its high throughput, scalability, and fault tolerance, making it a popular choice for handling those fire hose like data streams we talked about earlier.
And one of the things that stands out about Kafka is its distributed architecture, right?
Hmm.
How does that contribute to its capabilities?
So Kafka's distributed nature is key to its scalability and resilience. Data is partitioned and replicated across multiple brokers, ensuring that even if one broker fails, the system can continue operating without interruption.
So it's like having multiple copies of the data spread across different locations, ensuring that nothing gets lost and the system can handle a heavy workload.
Exactly, and this distributed architecture allows Kafka to handle massive volumes of data with low latency, making it ideal for real time processing application.
Okay, what about Apache Flink? It also seems to be a prominent player in the stream processing space.
Flink is a powerful stream processing framework designed for high performance, low latency data processing tasks. It's known for its ability to handle complex event processing and support for both batch and stream processing.
So it's like a versatile all-rounder that can handle a variety of data processing needs.
You could say that, yeah. Flink's flexibility makes it suitable for a wide range of use cases, from real-time data analytics and fraud detection to machine learning and event-driven applications.
And one of Flink's key strengths is its state management capabilities, right? How does that set it apart from other frameworks?
Flink provides, sophisticated mechanisms for managing state, allowing developers to easily store and access information that's needed for processing data streams. This is crucial for tasks like windowing, where you need to remember data from previous time intervals, or for implementing complex event processing logic.
So it's like having a built-in memory for the data stream, allowing the system to make informed decisions based on historical context.
Exactly, and Flank's efficient state management is one of the reasons it's so popular for building stateful stream processing applications.
Okay. We've got Kafka for handling those massive data streams, and Flink for processing them with low latency and complex logic. What about Apache Spark streaming? Didn't we talk about Spark earlier in the context of batch processing?
You're right. Spark is a general purpose distributed computing framework that's widely used for batch processing, but it also has a component called Spark Streaming that extends its capabilities to handle real-time data streams.
So it's like an add-on that turns Spark into a real-time processing powerhouse.
You could say that, yeah. Spark Streaming builds on Spark's core capabilities, like its distributed architecture and efficient data processing engine, and adapts them to the world of streaming data.
And because Spark is already so widely used, it makes sense that Spark streaming would be a popular choice for organizations that are already already familiar with the Spark ecosystem.
Absolutely. Spark streaming leverages the existing Spark, infrastructure, making it relatively easy for organizations to get started with, with real-time data processing.
So it's like a natural progression for organizations that are already using Spark for their for their batch processing needs.
Exactly. And Spark Streaming provides a familiar programming model and a rich set of, of libraries and APIs that make it easy to develop and deploy, stream processing applications.
Okay. Last but not least, we have Google Dataflow. What can you tell us about this tool?
Google Dataflow is a fully managed service for both batch and stream processing. It's like having a team of data processing experts at your beck and call, taking care of all the infrastructure and management tasks.
So it's a cloud-based solution
Hmm.
that simplifies the deployment and operation of stream processing pipelines.
Exactly. Dataflow is built on Google Cloud Platform and provides a serverless architecture, meaning you don't have to, you don't have to worry about managing servers or clusters. You just focus on writing your data processing logic, and Dataflow takes care of the rest.
That sounds pretty appealing, especially for organizations that don't want to deal with the overhead of managing their own infrastructure.
Absolutely. Dataflow is a great option for organizations that are looking for a scalable, reliable, and cost-effective solution for their stream processing needs.
So it's like a one-stop shop for all your data processing needs,
Mm.
whether it's batch streaming or a combination of both.
Exactly. And Dataflow integrates seamlessly with other Google Cloud services, making it easy to build end-to-end data pipelines.
Wow, we've covered a lot of ground in this deep dive into stream processing, from the fundamental concepts and architectures to the challenges, FAQs, and even the tools of the trade. It's been quite a journey.
It's a testament to the rapid evolution and growing importance of real-time data processing in today's world.
It really is amazing to think about how much is happening behind the scenes to make this real-time data magic work.
It is, and like you said, this is really just the beginning. The field of stream processing is constantly pushing boundaries.
So what's next? What trends should our listener, the learner, keep an eye on?
One thing's for sure, data is only going to get bigger and faster. We're going to need even more sophisticated tools and techniques to handle these massive streams.
Can our current systems keep up, or are we talking about entirely new approaches?
I think it's a little bit of both, actually. Existing tools like Kafka and Flink are constantly being improved, but we're also seeing new paradigms emerge. For instance, edge computing is becoming more and more important.
Edge computing, is that like processing data on the edge of your seat because it's so exciting?
Huh. Not quite. It means processing data closer to where it's generated, instead of sending everything to a central data center. The analysis happens right at the source on sensors, devices, even in your car.
So it's about reducing latency by cutting down on the travel time for the data.
Exactly. This is crucial for applications like autonomous vehicles, where split-second decisions are based on real-time sensor data. There's simply no time to send everything to the cloud and back.
Our sources mentioned smart cities as another area where edge computing is transforming things. What kinds of real-time insights are possible there?
Imagine a city where traffic lights adjust dynamically based on real-time traffic flow, or where emergency services are routed instantly to the most urgent situations. These are just a few examples of how edge computing enables smarter, more responsive urban environments.
It's fascinating to see how these technologies are not only changing the way we process data, but also impacting our daily lives in such in such tangible ways.
Absolutely. And as we, as we generate more and more data from sources like wearables, IoT devices, and smart infrastructure, edge computing will become even more crucial for managing this, this real-time deluge of information.
Okay, so edge computing is definitely one to watch. Any other trends on the horizon that you're particularly excited about?
The integration of machine learning and AI into stream processing is another game changer. Right now, we mostly use ML to analyze historical data, but imagine models that learn and adapt in real time as the data flows through the system.
So instead of just reacting to what's happened, we can predict what's likely to happen next and make more informed decisions.
Exactly. This could revolutionize everything from fraud detection to personalized medicine. Imagine a system that can predict and prevent equipment failures before they even occur, or a healthcare app that provides real time personalized health recommendations based on your ongoing biometrics.
Those are some pretty incredible possibilities. It seems like the future of stream processing is all about pushing the boundaries of what's possible, both in terms of technology and its impact on our lives.
I couldn't agree. I couldn't agree more. And the most exciting part is that we're really just scratching the surface of what's possible. As the volume and complexity of data continue to grow, so will the need for innovative stream processing solutions.
Well, on that note of boundless potential, I think we've reached the end of our deep dive into the fascinating world of stream processing.
I hope our listener feels inspired to explore this field further. Whether you're a seasoned data professional or just starting out, there's never been a more exciting time to dive into the world of real-time data.
Absolutely. And remember, there's a wealth of resources available online, from open source projects to cloud-based platforms to help you get started. Don't be afraid to experiment. Learn from others, and keep pushing the boundaries of what's possible with stream processing.
And who knows, maybe you'll be the one to develop the next breakthrough technology in this rapidly evolving field.
We can't wait to see what the future holds. Thanks for joining us on this deep dive into stream processing. Until next time, stay curious
And stay informed.